The series of Darwin Days talks here at the Museum of Natural History. My name is Ted Framd. I'm a paleontologist, retired with the U.S. National Park Service, and currently I'm with the Department of Geological Sciences and the Museum of Natural History here at the University of Oregon. And very happy to be here. I was asked to remind everyone for sure that the third lecture in the Darwin Lecture Series, which is, as you all know, Primate Perspectives, is next Wednesday, February 27th. The speaker for the third talk is Nelson Ting from right here on campus. Is he in the room by any chance? Oh, okay. I have not met him. And his talk is going to be on evolutionary guides to conservation strategies, presumably as relates to primates. So tonight's speaker, how to introduce him? Some of you may or may not remember a cult movie in the mid-'80s that was called Buckaroo Banzai. Anyone ever seen that? A few things. It was about a very inspiring but kind of irritating lead character who was, I had to even write it down what all it was. He was a nuclear physicist. He was a test pilot and race car driver. He was a brain surgeon and a rock musician. Our speaker tonight actually is one of those people. He is a surf bum that drops into conversation. Oh, I skipped that meeting and I went to go surf in Sumatra. Or, he ran yachts in the Caribbean, escorting the beautiful people around, and musicians like Neil Young and people like that. He was a king crab fisherman in Alaska, which you don't meet too often, and he just got back from gallivanting around Mount Everest for a period of time. But some years ago, he decided, okay, I've done all this kind of thing, I'm good at it. I kind of like fossils. I think I'll go get a PhD in paleontology and just see where that goes. And of course, he did. And now, if you go to any professional meeting and bring up his name, depending on who you talk to, you'll say, yeah, this guy, and they'll say, oh, yeah, he works on plesiosaurs. No, he's the one who described the oldest mosasaur, I believe, or ichthyosaur, oldest mosasaur. He described new ungulates from Florida. He worked on Pleistocene rodents. Someone else will say, no, he published work on the leatherback turtles from Antarctica. No, this guy, he worked on the Magneto Stratigraphy of the Escalante, and they're all right. Every one of these people. This is one of those Renaissance guys. So I hereby would like to give him a nickname, Buckaroo Barry.
Holy mackerel.
Okay, I'll make this quick. Okay, more seriously, Barry Albright received his Bachelor of Science in Oceanography from the Florida Institute of Technology in 1980. He received his master's in geology with an emphasis on vertebrate paleontology from LSU. What's the L stand for? In 1991. And the PhD under one of my mentors, Mike Woodburn, at UCal Riverside in 1997. He was a postdoc at the University of Florida from 1997 to 1999, where he actually did work on paleomagnetic stratigraphy of our beloved John Day strata right here in Oregon. After that, he was a curator of geology and paleontology at the Museum of Northern Arizona, and he's currently, Buckaroo-like, now with the Department of Physics at the University of North Florida, Jacksonville, Florida. Dr. Albright's talk tonight is titled North America's Last Non-Human Primate. And please save your questions for after the talk. Give a warm welcome, if you would, for Dr. Larry Albright.
Thank you very much. Is there even time for me to talk now, or did you? Just because I'm currently in the Department of Physics, don't get the wrong idea. I'm not a smart guy. I just happen to be in the Department of Physics because University of North Florida doesn't have a geology department. The earth science courses are taught through the physics department, so that's how I ended up in physics. Okay, so no, I can't go down the hall and talk to the guys that are doing solid state physics and electronics and things like that. However, I'd like to say it's a pleasure to be here. It's been a long time since I've been in Oregon. As Ted mentioned, I Worked out in the John Day for my postdoc from 97 to 99. But I'd also like to thank the Museum of Natural and Cultural History for inviting me here to give this lecture. It's particularly appropriate that I give this lecture on North America's last fossil primate here in Oregon, because it turns out that this exceptionally rare little mammal, known from so few specimens, is known from Oregon, from the John Day. A couple of these specimens are known from John Day. So this is the perfect venue for me to talk about Igemu wishashala. What I'll do in tonight's talk, is I'll sort of I'll start out by talking a bit about the rise and fall of primates in North America. Then I'll talk about a few hypotheses as to where this really enigmatic little guy came from. It's a mystery. There's not a lot known of this guy, a real mystery. And then we'll talk about how we know how old it is. Okay, first things first is learning how to use this pointer. Okay, so here we go. This is a sign that Josh has recently painted on the old Canton Ranch barn, pointing to sheetrock. This is sheetrock, and in fact, this is where some of the material has come from, up around the corner here. So, Igemu wishashala phyllotow is the name of North America's last primate. Reed McDonald in the early 60s described this little guy. It's Sioux for cat that looks like a little man, and we know it's about 28 million years old, and I'll talk about how we know that toward the end of the talk. The reason I use a picture of a tarsier is because the traditional understanding of Igemu wishashala's ancestry is that it is a member of the extinct haplorine group of primates called the Omomyoids, the tarsier-like, the extinct tarsier-like primates. The other side of primates are the lemur-like primates. The extinct lemur-like primates are the adapiforms. So like I said, the traditional view is that Igemu wishashala was a tarsier-like primate, so I'm going to use this little picture of a tarsier. Just recently, though, in some of the more recent literature, this picture might better be used. There's a paper that came out in 2010 that seems to think that Igemu might be an adapiform, one of these lemur-like primates rather than the tarsiiform primates. We'll talk a little bit more about that later on. There's only two places where Igemu wishashala is known from, possibly three. The type material was found in South Dakota in the early 60s and described by Reed McDonald again. Let's see here. And in South Dakota, only lower teeth are known. And this is, when you think of primate, think of squirrel size. This is a tiny, tiny little animal. It's not the size of a small monkey. This is more the size of a squirrel, tiny little animal. All that's known from South Dakota are some lower teeth. In the early 80s, John Rensberger found these odd little upper molars, and very primate-like, very small, no lowers, but John Day region and the section in South Dakota where the original material came from were similar in age. So we thought, well, maybe this is the same taxon, maybe this is that little primate Igemu wishashala, and he came to the conclusion that it was by taking these teeth and occluding them with these. Again, no lowers from John Day at that time. So he fit these to these, same size, they occluded perfectly, so he decided, okay, this is probably Igemu wishashala over here in John Day. It wasn't until the 90s that a lower tooth was found that confirmed that hypothesis. This tooth was found, this is the tooth found by John Zancanella in the mid-90s. Right, so this tooth was found up on sheetrock. It's the lower M1. So finally, there was a direct comparison between the lower teeth from John Day and the lower teeth from South Dakota. So in fact, Igemu wishashala occurs in the John Day region. In the late 80s and earliest 90s, I worked on a site in easternmost Texas for my master's thesis, the Toledo Bend locality. It was a really rich fauna, late Oligocene fauna, about probably around 23, 24 million years old. And I described the entire fauna, lots of ungulates and large mammals and small mammals, rodents, a micro-invertebrate fauna as well, snakes and amphibians and all kind of things. And in screen washing matrix for the small mammals and the small vertebrates, we came across this one tiny little really odd tooth. And when I first saw it, my first opinion was this has got to be some kind of weird squirrel, maybe one of the flying squirrels. They have kind of crenulated enamel like this guy did. And then I happened upon McDonald's 1963 paper describing Igimu washashla, and I said, gosh, this thing is so similar. It's got a lot of different cusps here and this crenulated pattern in the basin of the tooth. And so I sat on it for a long time. It's just this one single water-worn tooth. And I showed it to every time there was an SVP meeting, I'd carry it with me and I showed it to a lot of people, Dick Tedford and Malcolm McKenna, and they'd scratch their head and they weren't sure. And then I finally showed it to the true expert at that time in extinct Omomyoid primates, a guy named Fred Zalay, and he looked at it and he said, yeah, I think you've got perhaps not Igimu washashla phylatau, the type species, but he says, this looks primate, it looks Igimu, go with it. So with his blessings, I decided to go ahead and write a paper, and I published a little paper on Igimu washashla from the Gulf Coastal Plain in a Florida Museum bulletin. Josh and I looking at it again yesterday, you pull it out, and you scratch your head, and you just think, what is this thing? Is it really a primate? So I won't say a whole lot more about this guy. These are what we'll focus on most during the talk. And this is maybe 3, 4, 5 million years younger than these are as well. And there's this other interesting little Omomyoid primate that shows up in West Texas, and I just put the star and brought its name up to remind me to talk about it later. This is what's known of Igimu washashla. This is the type material from South Dakota. It's all a series of small little broken jaws with varying teeth in the jaws. This thing's about an inch long. The jaw's about an inch. Again, this is a tiny little squirrel-sized animal, okay, about an inch long. There's, I think, we counted today, a total of 5 jaws from South Dakota. So that's the South Dakota material. No upper material, no postcranian, no skull material, just these 5 jaws. And this is a composite drawing. This is a drawing based on a composite of a few of the specimens, showing most of the lower teeth. From John Day, we've got a P4, the original M1 that was found back in the 90s, and the M3. When were these other 2 found? When were those?
February of 2012.
So these are brand spanking new. This is kind of what prompted this talk, really. Brand spanking new teeth. And it turns out all 3 of these teeth were found in the exact same locality. They're all same preservation, same wear stage, probably from the same individual. So they've got to get back up there and find the rest of it. And these teeth were found how many years apart? 15 years apart, this tooth and then these 2 others. But you can see the M1 is a dead ringer for the tooth from South Dakota. The P4 is similar to the M3s. There's some variations. Is it enough to call it a different species, or is it just we don't have enough material to quantify or even qualify, for that matter, the amount of variation in this rare little beast. And this is the Toledo band tooth for comparison. All right, so let's talk a little bit about the rise and fall of the North American primate fauna. We go back to just after the KT boundary, right after the big asteroid that slammed into the planet. But the first part of the Cenozoic, the Paleocene period, it's still just a continuation of that same climate. Once the dust settled, continents hadn't changed positions. Ocean circulation patterns hadn't changed. So even into the earliest part of the Cenozoic, we're still extending that global greenhouse climate of the Mesozoic into the Cenozoic. So we've still got globally warm temperatures, high sea levels. There's still, contrary to this picture, there's still a South American-Antarctic connection. But by this time, by the early Cenozoic, Australia's already separated from Antarctica. India's on its way to a collision with Africa. Sea level's a little higher. South America's still separate from North America. But this is the world in which we'll see the first primates. This is the classic Zakos et al. 2001 oxygen isotope curve. That way is warmer, that way is colder. So here we are in the Paleocene, continuing that global greenhouse climate trend through the Paleocene. And it's in this warm greenhouse world that we see the first sort of pre-primates, the primitive pre-primates, the Plesiodeipiforms. So the primate precursors. Some phylogenies change all the time. Some workers place the Plesiodeipiforms as primates. Others just call them primitive primate-like eutherians. At any rate, that's what we have throughout the Paleocene. Here's the first North American pre-primate, Plesiodeipiform. It's called Purgatorius. It was found on Purgatory Hill in the Tulloch Formation in eastern Montana. The Tulloch Formation is the formation that lies directly above the Hell Creek Formation. The Hell Creek Formation is the last formation, is the formation that comes right up to the KT boundary. The Hell Creek Formation is famous because that's where the type specimen of Tyrannosaurus rex was found. The type specimen of Triceratops was found in the Hell Creek Formation. Famous formation. Purgatorius was found within just a couple of miles of those famous dinosaur localities in the overlying early Paleocene formation, the Tulloch Formation. Little rat, and doesn't look much different than a rat. So those have a holarctic distribution. They're found, these Plesiodeipiforms are found in Europe, Asia, and North America. Again, this is their time, the Paleocene. At the end of the Paleocene-Eocene boundary, an event called the Late Paleocene Thermal Maximum occurs. It's possibly related to the rifting of the North Atlantic, the opening of the North Atlantic, lots of CO2 in the atmosphere, so we get an even warmer world at that boundary. And it's thought that this increasing warming trend right here, together perhaps with the first occurrence of rodents. Rodents first appear in North America in the latest Paleocene. So these two increasing warm competition from rodents are thought to what led to the demise of the Plesiodeipiforms, the pre-primate, the primitive primate-like mammals. At any rate, that opens the door for the next flood of what Greg Gunnell would call the euprimates, the true primates. So extinction, a big faunal turnover here at the late Paleocene thermal maximum with the extinction of the primate-like mammals, and then the true primates show up. About 50 million years ago, 50 to 51 million years ago, temperatures have increased even further, and there's an interval referred to as the early Eocene climatic optimum. Still a connection. Again, I just mentioned that opening of the North Atlantic, but there still seems to be a connection from Europe to North America, from Asia to North America, because we find, again, this holarctic distribution of these euprimates, the lemur-like Adeipiforms and the tarsier-like Omomyoids. We're going to start seeing an influx of those forms into North America at this time. So here's what the mid-continent of North America would have looked like 50 million years ago. A lush, canopied tropical forest, an ideal setting, an ideal ecological environment for primates to flourish in and diversify, and they do. We see a great diversification of primates in this early Eocene time interval. So here we are. This is a diagram modified from the Gunnell paper in the big Janus and Jacobs volume, Tertiary Mammals in North America. Plesiodeipiforms in the Paleocene. They go extinct here. The Paleocene-Eocene thermal maximum. A rise of rodents, perhaps part of that contribution to that, perhaps contributing to that extinction. And then, several genera of the lemur-like Adeipiforms show up in the early Eocene. But more dramatic are all the Omomyoid primates that show up in the early Eocene after the extinction of the Plesiodeipiforms. Lots of different genera, lots of different species. The Omomyoids pretty much explode on the scene in this early Eocene tropical North America. And this is just another diagram that illustrates the same thing. This is from a paper that Woodburn and Greg Gunnell and Richard Stuckey published a couple of years ago, where they looked at the Paleocene through changing faunas as related to climate through the Paleocene and Middle Eocene. So again, here's your Plesiodeipiform, your primate-like guys who flourish in the Paleocene but go extinct at the Paleocene-Eocene boundary, opening the way for the Omomyoids and some of the Adapids, some of these other groups that are going to do exceptionally well during the early Eocene. All right, so we get through the early Eocene climatic optimum. Primates are doing spectacularly well, diversifying. Life's good for primates in North America over this interval. And then we turn the corner to about 50, 45 million or so, and we start this long, long climatic deterioration that will culminate at the Eocene-Oligocene boundary. We're going to see this diagram a lot. And this basically, this point right here represents the change from that global greenhouse world that had continued from throughout most of the Mesozoic into the early part of the Cenozoic. It ends here, the Eocene-Oligocene boundary, 34 million years ago, into what we call now our current ice house world. That obviously is going to have a dramatic effect on tropical adapted mammals, not just the primates, but all the tropical adapted mammals that existed in the early Eocene in mid-continent North America. A lot of that climatic deterioration that we see from this point on is due to the progressive decrease in the connection of Antarctica to South America. The Tasman Passage is already open. Australia is a good way from Antarctica by this time. But as soon as this connection is severed, that's the event that's really going to trigger, that's really going to end global greenhouse climate and trigger the beginning of this global ice house climate we're currently in. So this progressive decreasing is basically what we see here, slow deterioration of climate over the last 10, 12, 13 million years of the Eocene. 35 million years ago, we severed that passage, established the Antarctic circumpolar current, sent Antarctica into its deep freeze, so anything trapped on Antarctica this time, and by the way, I think by latest count, there are about 17 mammal taxa on Antarctica in the Eocene, but all having South American affinities, none with Australian affinities. The Nothofagus forest, so common down there in the Paleocene, early Eocene. Anything left on Antarctica at this point is doomed. We're going to send Antarctica into its deep freeze. This is going to dramatically, sets up the Antarctic circumpolar current, dramatically changes ocean circulation patterns, dramatically affects global climate, again, ending that greenhouse climate we'd been in from early part of the Mesozoic. So how does that affect primate faunas in North America? These are the Adapiforms. We can see that, by 35 million years ago, when the Drake Passage opens, when the connection between South America and Antarctica severed, at least the Adapiforms are long extinct. Let's look at the Omomyoids. Based on work of Beth Townsend and Tab Rasmussen and a few others in a paper just a few years ago, they looked at the faunas across North America, the early Eocene, determined that they were all typical of tropical forest. They were all mammals that would have been indicative of a tropical canopied forest. Then they noticed in the middle Eocene that there were that all the faunas had these transitional mammals that still had a few hangers-on indicative of a tropical forest fauna, but they were starting to see more and more mammals that indicated that, open woodland environment, these tropical faunas, these tropical forests were perhaps decreasing, perhaps contracting toward the equator, and that the mid-continent was opening up, open woodland, and then eventually to even savanna environments. So there's this transitional, centered on about between about 42 and 46 million, centered on about 45, they start seeing these transitional faunas, mammal faunas. You can see how depauperate the primate fauna is on the other side of this transition as climate changes across this boundary. And by the way, this climate change it's indicated by lots more than just the change in mammal faunas. I mean, plant fauna say the same thing. The oxygen-isotope record shows us this. Greg's work on paleosols in the mid-continent shows the same thing. Okay, so there's ample evidence that climate's changing pretty dramatically across the mid-continent of North America. So here at 37 million, we see the last of the North American primates. If we looked at the Adapiform, the lemur-like primates, same thing. They go out right at 37 million. That's it. They're extinct. They're gone. They disappear a few years before the actual opening of the Drake Passage, the establishment of the Antarctic Circumpolar Current. So, end of story. Primates had their acme during the early Eocene. They did okay for a while. By the late Eocene, end of story. They're gone. Or so we thought. So we've gone from the early Eocene to late Eocene. Basically, we've gone from this tropical canopied forest to more open woodland to perhaps sort of an open savanna woodland type environment. It just sort of occurs to me that this photo, we could call this photo the sun setting on the North American primate fauna. But yeah, but the environment's changing pretty dramatically. That's not to say that primates don't thrive in these more savanna, open woodland type environments. But these are entirely different beasts than the primates we're talking about, these smaller, much smaller primates. John Day region, 28 million years ago. The mammals show it again, the paleosols show it, the plants show it. We've gone from tropical faunas to these open woodland, tropical environments to these open woodland environments with forest, these riparian forests along the riparian corridors, frequent volcanic eruptions. So, and not exactly the kind of world you would expect, the kind of environment you would expect to find a primate. However, this is the environment, this is the time in which Ichthyosaurus shows up in the John Day. So, we've got the extinction of primates at 37. For all intents and purposes, they're gone. Done deal. Primates are gone from North America. And then, about 28 million years ago, here's Ichthyosaurus, this tiny little thing known from just all the fossils would fit easily in one hand. A real outlier, way out here, 28 million years or so, a 9 million year gap between the last of the great North American primate fauna and its appearance. This interval, this 9 million year interval, is not as though that's an interval that's not well sampled in North America. You got the Shadron Formation, the Brule Formation. I mean, there are lots and lots of sites across North America where this 9 million year interval is very well represented by mammals, and it has been for years and years and years, heavily studied, but no indication whatsoever of a primate. So where does this thing come from? How did it all of a sudden end up in an environment that it shouldn't be in? Why is it even here? Well, there's a couple of hypotheses. First of all, I kind of figured that I figured that if these guys could help the Egyptians and Mayans build pyramids and help build those big figures on the Nazca Plains that you can only see from a spaceship, that perhaps they knew that someday there'd be paleontologists on this planet and they'd kind of screw us up by throwing a little primate out there in nowhere. That's hypothesis one. Coincidence? I mean, look at the resemblance. I'm just saying. The other hypothesis, the other sort of traditional hypothesis that's been put forth until about a couple of years ago, till about 2010, is that Ichthyosaurus was the ancestors of Ichthyosaurus were near this little primate from West Texas called Runea. Again, remember Runea, just like the rest of these guys, went extinct 37 million years ago. But a few workers noticed that there were some similarities, that perhaps Ichthyosaurus originated or was derived from something near Runea. However, let's see what Zalay and Delson say about it. So early on, again, back in the 70s, the ancestry of Ichthyosaurus is very likely near the Omomyoid genus Runea. But then Zalay and Delson in 79 say, but its close affinities within the Omomyoidae are impossible to ascertain as most of its features are quite unique. This thing is just a real oddball, okay? A real oddball. Rosen-Rensberger in '83, when they described the John Day upper teeth, also noted the possible derivation of Ichthyosaurula from a form close to Runea. And then Nee, a couple of years ago, comes along and says Ichthyosaurula was first described as an Omomyoid primate, although it was always acknowledged that no Omomyoid actually resembles Ichthyosaurula in detail. The double-rooted P2 of Ichthyosaurula has never been observed in Omomyoids, although this primitive condition does occur in some Adapiforms. So I may have to start using the lemur-like picture to represent Ichthyosaurula rather than the tarsier-like picture. But again, Ichthyo was known from such little material. This is not definitive. This isn't the end of the story. It's going to change a lot, and it's going to change dramatically, obviously, when more material is found. So let's look again. Ichthyo is found here, Ichthyo is found here, Runea is found way down here at 37 million. Nothing else, no other primates found anywhere in North America that we know of until 9 or so million years later. So where was Ichthyo? The bottom line is we don't know. This is Runea. It's only known from the skull, okay? Beautiful little golf ball-sized skull from West Texas. But again, this is all we know of it. We don't have any lowers. So Runea can't be compared directly to Ichthyosaurula. I think the basis for saying that Ichthyo perhaps is derived from something near Runea was based on the upper teeth. Here's the upper teeth of Runea. But again, these are just sort of your generalized early primate low crown teeth, nothing particularly specialized about them. You look at the Ichthyosaurula uppers, similar. You know, actually, this is the P4. This is the P4. This is this tooth. This is partial M2. But again, very similar, just basic cusped pattern, low crown. This comparison is really what led to this broad idea that perhaps Ichthyo was related somehow to Runea. That's it. That's as far as they can take it. This is a figure from the Nee et al. 2010 paper showing several specimens of Omomyoids. This is the jaw of the extant flying lemur, the Dermopteran from Southeast Asia, Cynocephalus. This is a fossil. Primate that was thought to be possibly related to the flying lemurs, or the Dermopterans. And at one time, McKenna, in fact, placed Ichthyosaurula, this jaw right here, in with the flying lemurs, in with the Dermopterans. It's since been thrown into the Omomyoids. It's again, you know, the latest work considers it perhaps a lemur-like primate. But again, just look how different this thing is. It doesn't resemble any of these more common Omomyoid primates from the early Middle Eocene. Really, really an oddball. So we don't know much more. There's not much more we can do with Ichthyosaurula as far as determining its ancestry until more material is found. That's Josh's job. The government is paying him to find more Ichthyo material out at John Day, and I think they're hot on the trail. We really do. We need skull material. We need postcranial material that can be fit into these phylogenetic analyses with these other Omomyoids and Adapiforms for which there is much more material. That's the best we can do right now. So what we can figure out with a higher degree of accuracy is how old Ichthyosaurula is. It was first known, as I mentioned, from South Dakota, and it was found in a unit called the Upper Sharps Formation. It's in South Dakota. Its correlation across the state border into Nebraska. From that correlation, we know that it's probably about 28 million years old. Ichthyosaurula was found in sediments that correlate to Magnetocron 9R. This is a reverse polarity interval. I'll talk more about Magneto Stratigraphy in just a few minutes. But it's bracketed by the roundhouse rock ash above, the nonpareil ash, and the Rocky for ash below. These ashes all have good radioisotopic dates attached to them. So we've got a pretty good picture of how old Reed McDonald's South Dakota Ichthyo material is. Ichthyo comes from the John Day Formation. We know that they both have rocks of similar age. So the next question was, is the Igamo material in John Day the same age as that in South Dakota? The Rosen-Rensberger paper that described those upper molars of Igamo in 1983 noted that the material came from above the picture gorge ignimbrite, okay? And then they tried to correlate the location where Igamo shashla was found to one of Rensberger's rodent biozones. These have since kind of fallen apart. It definitely does not occur above the Deep Creek tuff. But again, all we know from this early work is that the original specimen is found from above the Deep Creek tuff. A few years later, Prothero and Rensberger went in there and using this new technique of Magneto Stratigraphy, decided that this was such an important region, the John Day is such an important region, that they should go in there, determine the magnetostratigraphy of the John Day Formation that would help date a lot of these fossils, not just Igamo, but a lot of the fossils that had classically come from this region for the last 100 years. Their they ended up with a magnetostratigraphy. The techniques used, we now know that the techniques they used basically resulted in noise. This magnetostratigraphic pattern really has no basis in reality. I hate to say that. Don knows this. I've talked to Don Prothero. He's not going to take offense if I say this. Also, he only had one radioisotopic date that he could use to pin his magnetostratigraphy to the magnetic polarity timescale. He had a date on the picture gorge ignimbrite of 26 million years. This was a conventional potassium-argon date that had been published by Vernon and Garnis-Curtis and some of the pioneers of radioisotopic dating back in 1964. So he had this one date on the PGI, and he had this magnetostratigraphy that he tried to correlate to the time scale based on this tie point. In the 1990s, a lot had changed. Ted had been at John Day for what, about 20 years by this point? Over 20 years? Okay, yeah. Several years at this point. And he and Eric Beslin and Greg Ritalik had gone in there and really straightened out the lithostratigraphy, which in retrospect is actually quite simple. No one had done it previously, but there are several units in the John Day Formation that are lithologically very distinctive. There's all these ash beds that are very distinctive. So understanding this now, it seems like how could they not have figured it out earlier? But understanding this, you can go to practically any place in the John Day Valley and find an outcrop, and based on the characteristics of those rocks, you can tell where you are in the section. So a lot was, this helped immensely. Rensberger and Prothero, they didn't have Ted et al.'s scheme to go by. Because of this new lithostratigraphic scheme, the mammalian biostratigraphy became much better understood. Now they knew where a lot of their specimens had come from. They could look at the matrix on the specimen, match that up with the matrix in the field, all kind of different techniques, but the bottom line is greater understanding of the biostratigraphy. A new technique of radioisotopic dating had been developed called argon-40, argon-39 single crystal laser fusion radioisotopic dating. Carl Swisher was one of the earlier guys to use that technique, and Ted was able to get Carl out to the John Day Valley, and Carl sampled several of the tuffs, including the PGI. He was able to redate the picture gorge ignimbrite as well, the only volcanic horizon that had previously been dated. New paleomagnetic techniques had been developed. We knew a lot more about the behavior, the magnetic behavior of the John Day rocks by this time than Prothero knew in his early study. And of course, by this time also, a new specimen, that lower tooth, that lower M1 of Igamo had been found. So we went back in to, with Don Prothero's graces, we went back in and basically completely redid what he'd done with this new information that we had at our fingertips. And this is the results of that work. So very briefly, magnetostratigraphy. just for those of you that are uninitiated, there have been times in the Earth's past when the compass would have pointed toward the South Pole, not the North Pole. And this flip-flopping of the Earth's magnetic field which occurs randomly. It doesn't occur like clockwork every million years or so. It's a total random process. It's recorded in sedimentary rocks. The changing polarity of the Earth's magnetic field is recorded in sedimentary rocks primarily because of ferromagnetic minerals like magnetite and hematite, these ferromagnetic minerals that act, to keep it simple, that act like little compass needles. So as these and they're pervasive. Ferromagnetic minerals are pervasive in the Earth's crust. So as rocks erode, as sediments accumulate in basins, as they settle to the bottom, these grains sort of align themselves like little compass needles with the Earth's magnetic field. And as that sediment is lithified into sedimentary rock, those little compass needles are locked in. So we can go out in the field, we can sample the rock, throw the rock in a really fancy magnetometer, and the magnetometer will tell us if those rocks were laid down during a period in the Earth's past when the compass pointed toward the North Pole or the South Pole. That doesn't give us a date, but in concert with a radioisotopic date from these ash beds, we can use that, just like Prothero did, to pin our Magneto Stratigraphy to the global magnetic polarity timescale. So this is how it works. This is a section out of the John Day Valley. We tried to sample, here I am hacking out some rock. We tried to sample about every 2 meters over the entire 500-meter section of the John Day formation, John Day and Kimberley formations. And here's sort of how it worked. We apply, Ted comes out with us. He tells us where we are in his lithostratigraphic scheme, unit G, unit H, unit I, unit J, and so forth. We pop the samples out, we take them to Berkeley Geochronology Center, and we determine the magnetostratigraphy for that section. Black is normally polarized, compass pointing toward the North Pole. White is reversely magnetized. So in this particular sequence, we see that most of unit G is normally magnetized. These rocks were deposited during a period in the Earth's past where the compass pointed toward the North Pole. These rocks in unit H were deposited during a period in the Earth's past where the compass pointed toward the South Pole, and so on. So now that all we have is this magnetostratigraphic pattern, normal, reverse normal. That gives us nothing. That tells us nothing about where we are in time. However, the picture gorging nimbrite is right below us with one of Carl's argon single crystal dates, not 26 million years anymore, but 28.7. So obviously that's going to affect the correlation that we have versus the correlation that Don Prothero had when he only had a 26 million year date. The Deep Creek Tuff lies above it, so we've bracketed this sequence very nicely. Deep Creek Tuff at 27.9 million years. So now we've got our magnetostratigraphy, we've got our radioisotopic tie points, and we can fit this magnetostratigraphy into the time scale, into the magnetic polarity time scale. It turns out that this reversed interval correlates to magnetocron, reversed magnetocron 9R, at about just a little older than 28 million years. So we've got these dates 27.9. We know this is about 28 right here, 28.7 here. Gee, it works. All right, in case you didn't catch that, we're going to do it again. Ready? Lithostratigraphy. Magnetostratigraphy. Dates. And then our correlation. So we know that we've got this long interval of normal polarity that it contains the Deep Creek Tuff and the biotite tuff. Above that is this interval of reverse polarity. It's got to be 8R, and that's how the game works. So we're able to build very high resolution. We've got lots of ash beds out here. That brackets that's pretty good. That allows us to bracket our mammals between the dates of those tuffs. But this allows us even further, this provides us even further resolution. So we really are able to develop a high resolution, refined temporal framework for anything that happens out here, not just which mammal, where the mammals occur in time, how long they last in time, but tectonic events, anything else that might wash into a basin that you want to date. Here's your temporal framework with which to do that. This is just a lab at Berkeley Geochronology Center, cryogenic magnetometer, run by a 25-year-old Mac which crashes regularly. And this was the results of our study, really. Numerous sections overlap some sections. Some of the rock didn't behave well. Some of the rock behaved extremely well. So we ended up with this correlation. All right, so what's that got to do with the age of Ichthyosaurus? This is a diagram that Josh provided for me. In John Day, Ichthyo has only been found in unit H. That's not to say it won't eventually be found above H or below H, but so far it's only known from unit H. Unit H correlates to this magnetocron right here, right about 28 million years. We know that Ichthyosaurus in South Dakota occurred right about 28 million years. So they occur in both areas at the same time. That's a good thing. Biochronology works, all right? Also lends a little more confidence to the idea that the species of Ichthyo in Oregon is the same as in South Dakota. There's a few little changes. I don't know that we'll go that far out on a limb, but it certainly provides, gives us a little confidence that we're looking at the same species. This is just, again, I mentioned the word biostratigraphy. Now we can take all those mammals that have been collected in John Day over several years, particularly with Ted there the last several years, collecting the mammals in the context of this well-understood lithostratigraphic scheme. So now we can play the games. Okay, these guys are only found in this unit. These guys are only found in this unit. We've got a really high-resolution temporal framework within which we can place the mammals. We can compare their first arrivals and last appearances with that same data in other parts of North America. That's really how the game works. Let's see. I think that's it. This is what I'm hoping will eventually happen. There's a few characters in this picture that are here. Here's Ted and Skylar, Sam. Here's Kristen and Josh. Good grief, get a room, dude. Well, let's see, Mike Woodburn, Dick Tedford, Dave Whistler. Anyway, I'll end the talk there. Thank you. I guess the take-home message really is this is such a poorly known little primate. It's such little material that its ancestry is going to be argued for a lot longer. We need more material. Same old story in paleontology. We need more fossils. And it couldn't be truer in this case. So we still have a long way to go. We know where it occurs in time. We know where it occurs in North America, but we have a long way to go before we know where it came from. Thank you very much. Okay, I'll try a few questions if anyone. Sure.
How could the Indians have a name for this beast when it was long extinct before any humans arrived here?
What a great question. The Indians didn't have it. Oh, okay. How did the Indians have a name for it? I gotcha. Well, I just learned that story today. It turns out that during the Civil War, was it during close of the war, Custer times, there was a Union soldier out in the Sioux Nation area who had a little hurdy-gurdy monkey. And the Sioux had never seen this thing. They'd never seen a monkey before. So they called it the little cat that looks like a man. Reed McDonald, knowing that story and knowing some Sioux vocabulary, applied that name to this little primate. Great question. Next. Of course.
If it were a Demopteron, let's just say, does that make the problem worse or better? I mean, we don't have much of a record of Demopterons, do we?
No, I'd say worse.
It makes it way worse.
It makes it a lot worse, yeah.
What do we have with Demopterons?
Well, that thing called plagiamine, I think plagiamine from Alberta, maybe southern Canada, I think it's still considered Demopteron.
That's all we can see.
But no. It's Middle Eocene. Plagiamine's from early to Middle Eocene, yeah. And I don't even know if that's still considered a Demopteron anymore. I know McPhee years ago, he didn't think it was a Demopteron.
There are some from the Aleocene of Asia.
Oh yeah, Southeast Asia, sure,
So
but North America, no.
And we have that bat from United Hills, remember the Royal Brown years ago? Is that a Demopteron?
No, it's not a bat.
It's a regular bat.
Yeah. Interesting that you mentioned that. I just read a paper recently. God, who was it? I can't remember, but someone was placing Dermopterans closer to bats than to primates. I can't remember the paper. So again, it's still a big mess, Greg. What's that?
McKenna's latest.
No, I think it's more recent than that.
There's just some genetic studies.
Say that again.
There's just some genetic studies with it too.
Oh, okay. What else? Amy?
Have you looked at has anyone looked at the shearing quotient or estimated the diet
I don't-
of baby?
Well, frugivore. You know, I think that's the conventional wisdom for Igamo, but no, I don't think anyone has it. Or I don't know that. Say it again.
Insectivore at all? Like some of the
Doesn't seem like with these bunodont cuffs, these low bunodont cuffs. Doesn't seem like it. But that that brings up another question. I wonder if anyone's looked at the microwear or mesowear on those uppers and lowers also. That's a great project. Maybe that's waiting for you to do.
There is a creature in Africa, the bush baby, that lives on tiny little trees, and they're just fantastic when you go out with a flashlight. You see all these little eyes, and these bushes that are no bigger than a human, in pretty dry country.
We had this conversation this morning.
Well,
You just think,
it's not,
well, you're talking, if you look at the environment that Igamu's in, the taxa it's found with, burrowing beavers, no evidence of trees, amphispenids, all these burrowers in Unit H. Yeah. So is this thing living in shrubs on the ground? I can't imagine something like that.
Well, it depends.
Yeah.
Low little critter.
Right.
But it depends what Paleozoic came out of, because there's a bunch in there. Some of them did have trees that would have been human-sized,
Okay.
2-meter trees, little bushes.
Right.
Yeah, so it wouldn't be unusual. And some of those trees
But where
have nice fruits to them. That's
Sure.
that's what it lives on.
Yeah, absolutely, yeah.
The little berries.
What preys on the ones in Africa, though? Are they easy?
Anything is
Really?
the spears, whatever it is.
Okay. Really? You get whacked out of the tree?
They live in the cavities of the trees, and they'll use the spears to
Just poke them.
poke them.
Gotcha. Wow.
I think it was probably like Gollum and fish.
Oh yeah, fish. Went down the Sunday River and grabbed fish and then beat the fish over the rock. Yeah. But it's like I keep emphasizing, we know so little about this guy. Yeah. And it is odd. It's way out of it's anomalous from a temporal perspective. It's anomalous from an environmental perspective. What's it doing there? Hi. Yes.
So what happens if it's in the data report? So you.
I use a different picture.
You throw this out. Well, yeah, but I mean, you threw this out as a hypothesis. Like, if that's true.
Oh no, it's not my hypothesis.
Apparently, it fixes the P2 problem, but like, what does this do to the whole spectrum of like characteristics? Does it match like crap with everything else? Or
No, it still does. I mean, so there's a P2. There was the hypo. Yeah.
Hypocone
Right.
is another characteristic that it shares with the data forms.
Yeah. So maybe that's.
I mean, does that fix it? Is this one of those like aha?
I don't think so. No. I don't. I don't think it's going to. I don't think it's going to be fixed until more material, until the skull's found. Does it fix it? I think to some extent it will make more sense, but it doesn't fix it. Yeah, that's a good question. What else? Okay, thanks for showing up.
Thank you.
Next time I talk about it, we'll have more.